I even brought demos in today here. So we were talking about the PN junction diode. Next time we're going to talk about, so we are going to start talking about transistors today. There's not much written in your book. There's not too much to say. We're going to say about transistors. You'll learn more about transistors when you take the electronics class. But read about the transistors and read about superconductivity. That's what we're going to talk about next time. Okay. So we've been talking about the PN. It's called the PN junction diode. Can you see that? Because I can't even see that up there when I'm standing there because of the glare. Okay, so we make this junction out of a p-type, and we know how to make a p-type semiconductor and an n-type. Just over here, I'll remind you for the p-type. What we are doing is making the mobile carriers these things called holes, right? But really what you're doing, just to remind you, is you have your valence band for your semiconductor, and by putting in every once in a while a atom that doesn't have as many electrons, you're creating this vacancy that we call a hole that can move around as electrons go fill it. Do you remember that discussion? So what you're really doing is, as far as talking about energy, you're creating places because the electrons don't need much energy to go fill these holes to move around. So you're creating little energy levels right above the valence band. So an electron, when it goes fills a hole, there's a little bit of energy there to do that. Okay? So we call those acceptor levels. I don't think I said that. So they're called acceptor. They'll accept an electron. But when we make an n-type, semiconductor, this is our conduction band. We have the valence band down here, and now we're putting in materials. We have an extra electron, and that extra electron is not really tightly bound to any local atom. It can move around pretty easily. So what we're doing is we're putting these electrons in, and they have energies right below the conduction band. So, and we call those donor levels. Okay, just a review there. For the PN junction, we have this interface, which is never very clean. We always draw a line, but of course it's not that nice, right? And then we have, even if we have no bias, if we've not connected any battery to it whatsoever, we still have what we call the depletion zone, right? Where we've had electrons on the N side that have moved over and recombined with holes on the other side. So you have this region where you've had these, we call them recombinations between the electrons and holes, and you don't have any mobile carriers in that region, anything that can move. Okay? So you have this depletion region. Where there is no mobile carriers. Now, you might might still get an electron, let's say, go over. There's some probability that an electron over here might make it over. So even if I connected a wire there to each of those sides, I might get some current, let's say. Okay, let's call it I naught. I get some little bit. How much current, how many electrons do you think would jump over there? Well, there's an electric field that's created here, right? We said that because when those electrons that were here, they combined with those holes here, this thing was electrically neutral. But now, we've moved electrons over here on this side of the junction and holes over on that side of the junction. And what happens is now, since that was electrically neutral and you've gotten rid of electrons, this becomes positively charged, this becomes negatively charged instead. This in this region. We created an electric field in there. Okay? So there is a voltage, a potential difference across that barren area that we call the depletion region. Okay? There's a voltage across the depletion region. And what I said was you set up an electric field there, but that's true. If you have an electric field times some distance for the depletion region, that's the voltage. Okay? So we'll call that V, that voltage. It just sets up there just because you put the junction together. Okay, we'll just call that voltage. So the electrons that might jump over that, the electrons want to go in opposite direction of the electric field. This electric field goes this way. Okay. Electrons want to go that way. But once in a while, an electron might get over there. The probability that it's going to go over, number of electrons that cross the depletion region. R, if you want to, think of it as the number of holes that go the other way. It depends on, well, it depends on how many holes and electrons you have in the first place, right? If you had 0, there's none that are going to cross. So it depends on the number of charge carriers. So this is the number of charge mobile carriers. And then it exponentially, as this gets more and more voltage across here, let's say it does that by the distance getting bigger or something, as the voltage increases, there's less likely chance the electron's going to make it over, right? It has to cross a bigger voltage. Remember, how much energy does something have to require to go over a voltage difference? How much energy does a charged particle have to move across a potential difference?
Is it voltage over distance?
No, that's electric field.
Oh.
Energy. If I want to give something, if I have parallel plates, yeah, if I have two parallel plates here, and this is positively charged and this one's negatively charged, and I want a proton or something positive charge to go from this plate over to here, and there's a potential difference V there. This has charge Q. What is it?
Is it times distance?
It's just QV. Yeah. It's just QV. That's the energy. Energy required to go across a potential difference. Okay? Or energy gained if it goes the other way. If I have my positive charge here, it wants to go that way, it would gain an energy of Q times V. Okay? So energy to go across potential difference. I know that stuff was a long time ago, so. Okay, so the probability is going to decrease exponentially depending on that, how much energy you need to go across there. And it's going to be this Boltzmann factor. It's going to be, that's how much energy you have to require for the electron or our whole positive charge there, over kBt. kBt is our approximation for the thermal energy that's available, okay? kBt, remember something like a gas particle, ideal gas, if it's in 3 dimensions, it has 3/2 kBt of energy, kinetic energy. But the particles here in this solid, you can't really necessarily treat them like an ideal gas in 3 dimensions. So we use kBt as the approximation for the thermal energy available, okay? Approximate thermal energy. So if the temperature was very high, and you have this kBt in here, it's going to make it more probable that you can get things across. So that kBt down here is fraction here, okay? Or if you make V very small, it's more likely it's going to get across, okay? So, there we go. So what we expect then from looking at this sort of probability is that the current you might expect goes like this, and we'll call the current, we'll say the current you might have. Now let's wait, let's talk about, we add the fact that what happens when we actually put a potential difference, a bias on this. So if we put a bias on there, so that's with no bias. I don't have a battery connecting the N side and P side of this, okay? But let's put a bias on, let's forward bias this. That means you put a positive side of a battery on the P side, negative side to the N type. So this is forward bias. Okay. So if we forward bias this thing, what have we done here? So we talked about the fact that we shrink the depletion region, right? We talked about that last time. So what's really happening? So when you had no bias, you put no battery on this thing, there was a certain potential difference that electrons had to jump over to get across, get over the other side, right? But by putting this battery on, what you're doing is, and we'll call this bias, is the bias voltage. What you're really doing is reducing that potential difference across there. So the potential difference across this junction now across this depletion region would be what you had before. Minus this bias voltage you put across there, right? So it turns out then, here's how you would expect more to be able to get across, because you would have this, and instead of just V up there, I put V minus. Okay. And you could write that like this. Oh, I forgot the total number of mobile carriers. So then you get this, N equals the number of carriers times this is supposed to be over KBT2. Okay. Now, I'm almost ready to write a current here, okay? So, this is what we had when we probability to get across when we didn't have any bias voltage, okay? So what we're gonna say is we've increased the probability, so we ought to increase the current that goes through too, right? By this factor. We've increased the number of carriers that can get across by this factor. So we increase the number of carriers that cross depletion region by this factor. So I'm going to make the argument that we ought to increase the current, because this would lead to a current, a very small current. Okay. Small current. So we ought to increase the current by that factor. So here's what I'm going to say. Write it over here. So the current ought to go as some sort of base current. This will be the current, this I naught will be the current if you had no bias. Current with no bias. This is related to the number of carriers times e to the negative. Okay? That would be the voltage you had across that junction without putting any bias voltage on it. So that I naught's related to that. And then I'm saying we're going to increase it when we put a bias voltage on it by that factor. Before I finish the last little bit, I want to see if there's any questions, or if conceptually you understand this, or if I completely lost you.
Would you mind going through the units of e to the negative EV over k AT?
It has no units. This has units of energy. In the EV, this has units of energy.
Okay.
So there's no unit. It has to be. Can't have that.
So it's just units, so we're pretty much just scaling up the current then?
Yes.
Okay.
Yeah. By this. Yeah.
Yeah, and that makes sense.
So I'm not saying that this ratio number of carriers e to the negative v over kV, I'm not saying that's a current. We're saying it leads to a current. And let's call that current just by them being able to randomly jump over once in a while. Let's call that current I naught. Okay? And then I'm saying now by putting the voltage across that, we're reducing the voltage they have to cross by that bias voltage. So that has by looking at the math, that has what we're really doing is increasing the current by that factor. Now, that's not all there is to the story, because you still have, even though you put this forward bias on it, and you're making it easier for electrons to go over here, every once in a while you have an electron that was over here, it'll go back, right? So before, when I said you had that I naught, that you had a probability when the electron could go over, you also had the probability the electron could go back too, okay? So you would actually expect there to be no current at first when you hooked it up, because it would be equally likely the electron might jump back too, right? Matter of fact, maybe even more likely. Right? So you expect that we're missing something here for this current. The fact that holes and electrons can also just jump back randomly. So what we do is we make the total current look like this, and we could do they do a more detailed analysis than what we're doing. We're just making arguments about this. Say the total current is some sort of this base current E to the bias voltage over kVt minus probability it might just jump back too. Okay, so we get this. And then you can factor out this, what we're calling this base current. So you can write the current should look something like this. And this makes sense. This is your net current, forward biased. Oh, any bias actually. If you look at this, let's make this the bias voltage on this axis, and this axis is the net current you have. Really, this thing is going to look exponential as you increase the bias voltage, right? It might not start at 0 here, but it's going to go up exponential. Okay. Actually, it's going to be really close to 0 because this is going to be small. So it's going to look something like this. And then what happens if you go negative? If you go to a negative, so here's 0 bias voltage. What happens if you go negative? If I make that negative, very quickly, it's not going to take long where this just looks like negative I naught. Right? Because that's going to be a negative up here. Make that bias voltage negative. It's going to look like this. And it's going to eventually saturate to this negative I naught down here. We call this the leakage current. So we call that I naught the leakage current. So you might get again, when you reverse bias it here, you might get a little bit of current, but not much. But you get a big increase as you change the bias voltage if you forward bias it. So that's the basics of the PN junction diode. And if you remember, I told you the symbol for it is this. This is the cathode side, meaning that's the N type. This is the anode. This is the P type. And if you actually have a cylindrical one like I showed you the other day, there's usually a little band here that tells you which side is the cathode and which side is the anode. So I have one here. I brought one of those in. And I thought we'd just test it. I have a little amp meter here. And let's see how it changes as we change the bias voltage. Now usually, by the way, so how I'm going to hook this up is I have my PN junction, I'm going to forward bias it, but I'm actually going to put a resistor in here, like a 270 ohm resistor here, and then I'll put the positive and negative here. The reason you put that 270 ohm resistor in here is this thing has very little resistance. And if I put a voltage here, even if I put 2 volts, and I have very little resistance, I can get a lot of current. Remember V equals IR, right? If I have very little resistance, I get a lot of current, I'll heat the wires up and burn them. You don't want that. So you always put in a resistor here. Okay? So let's see what happens. Why don't you just come up here? It's easier to. I'll show you how we hook this up. So here's my diode. This is the cathode side here. This is the anode side. This is the positive side. So this is the side I want to be plus. Okay. I'm going to run it first through this ammeter, see if we have any current. So I'm going from the positive side of my battery here, to run through this analog ammeter. You got to have it connected, right? The positive side of it goes closer to the positive side of the battery for these little ammeters. So I'm going from there. Then it's running through the ammeter, the current is, and then I'm going through the resistor to the positive side of that diode. Okay, so this is called a breadboard. I don't know if you've worked with these before. So see that slot across there? That breaks this, but anything that's on this row is connected. Then there's a break, and anything over on this side is connected. So I attach it to this side of the diode. This side of the diode now I want to go back to the negative side of my battery. So the little thing, I'll just connect there, connect to the negative side. So I think let's keep track just to see what it looks like. And I'm going to we'll make up some units here for the current through this. So turn on. Now, we might not get any current for a little bit. Oh, I'm probably going to plug it in. Okay. So, okay, 0, and move until we start to get something. Oh, there we go. So we're getting here 1 milliamp. Roughly at 0.7 volts. So I'll make this unit 1 milliamp. I get 1 at 0.7. So what if we go up to 1.4? Twice that. We should get more than just another milliamp, right? If it's exponentially increasing. So let's go up to 1.4. What did we go up? We went up not till 2, but we went to 2 point what?
Oh, 3.3.
Well, 3, yeah, 3.3. I think that's about right. So we're at 1, 2. We're up here. So we were here for the first one. So then, what if we jump up by another 0.7? That'll be what, 2.3? 2.1, yeah, 2.1. So what do we expect? I mean, this is going, so let's go up to 2.3. So we're over at almost 7, right?
Well, here's 1.1.
Oh, 2.1, you're right. Well, I had a second in my head to have. It's hard to get this straight. So where are we at?
6.2.
2. So yeah. If we apply that, we would see that that's a pretty good exponential fit. So now, the other thing I have here, that we'll talk about in a second. So yeah, it increases exponentially as you increase that bias voltage. So, and if you reverse bias it, let's change the direction for this. Then I'll change the direction of this. We're getting nothing. You might see the needle goes basically nowhere. So when I reverse bias it, I can't, at least I can't see it on this. If I actually got a ammeter that measures in microamps, I might see a little bit. But since this is milliamps, I'm not going to see anything. So I increase that voltage. So nothing going the other way. So it's a good switch in that way. This is another. This is, and we'll talk about this briefly. This is a LED, a light emitting diode. So a light emitting diode, I'll tell you what the symbol is in a minute, but it has a long leg on them and a short leg. And I have the long leg bent on this. Actually, I have. I'm going to want you to look at this. So a few people take one of those, and I'll show you when you get back to your seat. We'll look at these. But the anode side is the long leg, cathode. So I should be able to do the same thing, right? Take and put the anode side next to the resistor. I want that to go to the positive side. So I've got to replace these again. Have the, changed everything here. Positive side of the battery goes to the resistor. This. So the current flows through the resistor, then from the positive side to the negative side. So if I put this on here. So again, I should, if I reverse the current, I should get nothing out of this, but this is forward biasing it again. And I get nothing. And I start to, I get, looks like no flow of current through there until I reach a certain voltage. About 0.6, you probably can't see it. I'm starting to see a little, as I go on up, I can see it. You can see it glowing pretty good there. But you get nothing on here until you get to a certain voltage. And then you start getting current, you start seeing it light up. Okay? So we'll talk about why that is. Anyway, I don't know if I have enough for everybody, but going back and we'll talk about the LED here a little bit. Talk about the transistor. So also with the LED, you want to put a resistor in the circuit because you'll burn it out and you'll burn wires. Actually, you won't burn the wires with an LED. You'll burn it out actually before you get too much current. So light emitting diode. So the symbol for that just looks like the diode symbol except for this. You put, actually they usually just use straight arrows just to represent light coming out of it. Now, if you look at the one you have, they're in the transparent case so you can, so light will come out, but they look like this. So you have your case, and if you look in there, it probably looks something like this. You have a thick part, and then you have usually a pretty thin part. Looks something like that. The thin part is the anode, and it has a longer So, and then there's this cathode. Now, generally how these work, I don't want to erase this, I want to use these. Yeah. When we forward bias, it makes it easier for electrons to cross the junction and for the depletion region, and for holes to jump the depletion region. So you have this, I'll draw it like this time, positive, negative type. And we have this depletion region, so you have your holes that are crossing over, and you have your electrons that are crossing over. And what we do is make the region in between the p-type and n-type a little thicker. They actually put in usually some other material that they call the active region. They just make it so that it's likely there's more chance that the electrons and photons will actually recombine before they cross all the way over. Okay? So you make it so we're forward biasing, plus minus. Make it more likely the electrons and holes recombine before crossing depletion region. So they combine in here. Now what actually is happening as far as if you think about energy when that happens is you have, this is your p-type, this is your n-type, okay? You have your electrons up here in these donor levels. You have these acceptor levels here. So when I say an electron in the n-type is recombining with a hole in the p-type, what's actually going on? Roughly it's this. Electrons going down to where the hole energies are, okay? This is recombination. So there's an energy difference here. It's basically the energy difference of the band gap, because these levels are right below the conduction band and these are right above the valence band. So the recombination energy is roughly the band gap energy, roughly. Okay. So recombination energy. So the electrons lose that energy. They were up there by the conduction band, and they've moved down to a lower energy level. Okay. Electrons lose energy from donor levels to the acceptor levels. So that difference in energy is approximately the band gap energy. this energy loss is approximately the band gap energy. To a good approximation, okay? Is there any question about what I'm saying there? Okay. So, what happens when an electron at a higher energy level in an atom goes down to a lower energy level? It has to release energy and momentum, actually. It releases it as a photon. Okay? So when this happens, you emit a photon. And if that energy band gap is at the right energy, that photon will be in the visible range. Okay? So yeah, we have basically this. The energy of the band gap is approximately equal to then so we could, in the visible range, I mean, you're limited because you have to make this stuff out of semiconductors, right? You can't just make any wavelength you want. Nature has restricted us by not having certain semiconductors. And you play around trying to dope, you know, gallium with different stuff or silicon with different stuff to try to change that band gap so you can use this stuff. So we could make red very early on. We could make green. Then that was the second one we could make. And then eventually we can make blue. In the visible range. Now once you can make blue, that was a game changer because you can combine blue, green, and red to make white. Okay? So you can combine those to make white. But white LEDs that you buy now, the good ones, are not made with just blue, green, and red LEDs combined together. Instead, how white ones, the better white ones, meaning it looks brighter, looks like cleaner white light. This white light doesn't look very good because it's only made from 3 different wavelengths, basically. Better white LEDs come from this. You have a blue LED and a fluorescent material that you coat the inner of that capsule with. So you have that capsule, you have your blue LED, and then you have this fluorescent material that coats the inside of that. So what does a fluorescent, we talked about fluorescent briefly. You hit it with light, then it creates light at a longer wavelength, right? So what happens is if you look at the spectrum, this is wavelength, and this is intensity. You'll get a peak at the blue, like 465 nanometer. We see between 400 and 700. 700 is the red, and violet is 400. So you'll get this peak around here, and then you'll get from the fluorescence this wide spectrum, and they'll combine to make white. Okay? So that's from the fluorescence, and this is from the blue. But they're a lot more efficient, right, than filament lights that we have where you just heat them up and you're losing most of that energy as heat. Here we're not. And now we can make them pretty cheap. So now, so that's a light emitting diode. Just so you know, what we call a photodiode takes in light, and you can use it as a sensor, okay? It works the exact same way, you just go the opposite way. Electrons go from up here to, from the valence band up to, back up to the, near the conduction band. So basically you have light coming in, and you take electrons from the valence and you move them up to the conduction. Okay. So these are light detectors, and they work at different wavelengths, of course. Your photons at a certain wavelength have to get across the gap. They have to have enough energy to knock electrons up there. And the symbol for this thing looks like this. It's a diode. So it has that symbol, and now you just put the light coming towards it instead of away from it. Okay. I'm just going to introduce the transistor here to you. It's kind of a shame we don't do more with the transistor because it's the biggest cultural changing device, electronic device we've ever had, right? It's changed everything, right? In your computer chip, you have billions of these things. So they act as switches, they act as amplifiers. We use them for all kinds of things. And before them, we only had vacuum tubes that did the same thing. Okay, and we had a heated filament. Electrons come off that filament, and we accelerate them. And how much we accelerate them, we have more current. You accelerate them higher energy, and so forth. So that's vacuum tubes is how we amplified things. You turn on, we still have old devices around here that have vacuum tubes in them. I have in my lab downstairs, I have my great-grandpa's old radio from the 20s, and it has vacuum tubes. You turn these things on, you have to wait a little bit because the filaments have to get hot, everything has to get warmed up before it starts working well. So it doesn't take that long usually, but it takes a little bit of time, and it produces this heat. Well, then they came up with these transistors that don't produce any heat, and they work instantly. You don't have to wait for them to warm up. So you just turn on your radio and you immediately have your sound. When I was little, they still had radios that would come that would still say transistor on them. Now, they don't bother with that stuff now, right? But I remember getting my first little transistor radio. It was great because I could listen to ball games in bed at night, you know. Have your little earpiece in so you wouldn't get in trouble if you listen to the radio. You can sneak it into school and stuff. So I'm going to just give you an idea how a transistor works. And maybe talk about it a little more. We actually might watch a little video about the transistor because it really is culturally important. So what I'm going to talk about is called the junction field effect transistor. And this transistor was actually invented in 1947. By a guy named John Bardeen, Walter Bratton. I think he taught for a while at the school that Pedler went to, Reed College. Bardeen was at the University of Illinois after all this, and then William Shockley. Shockley started. So all three of them worked at AT&T Bell. That's where this happened. And after this, there was a lot of disharmony among them, and Bardeen and Bratton quit, and Shockley moved on. He went to California and started Silicon Valley. He was the first electronics company in Silicon Valley. He was a terrible manager. Nobody liked him. He wouldn't stay on focus for anything. He had a lot of brilliant ideas, but that was the problem, right? He would have this idea, okay, we're going to do this. The next day he'd come in, no, we're going to do this. Next day you couldn't make anything if you have somebody that's running the company like that, right? So eventually his group of employees said, we're quitting, we think this stuff's important, we're going to quit and make this ourselves, these transistors. So they started a company called Hewlett-Packard. So anyway, the junction field effect transistor, the basic idea is this. We have a p-type material and an n-type material. And we could change these around. We could make this n-type and make this p-type. This one's going to be called, we're going to call this an n-channel. Now, this is n-type material. This has mobile electrons in it, right? Mobile electrons. So if we hook up, and it's a big side, the p-type's small compared to it. If we hook this up to a battery, which we'll call this, I'll tell you why here in a second, BDS, we're going to get current flowing through this because we have electrons in here, right? We're going to get current, assuming it's going from the positive side of the battery to the. Okay. Now, there is a depletion region, right? Because I have this junction. We know about p-n junctions now. I have this depletion region here between the n-type and the p-type at their junction. So this is my depletion region. What happens if I forward bias that now? Or reverse bias it. That's actually what I want to do. I want to take this, here's my p-type. Here's my n-type. I'm getting current going through here, because I have that. But what if I reverse bias this? What if I put a negative and a plus there, between the n-type and the p-type? What happens to the depletion region when you reverse bias? Does it get smaller or does it get bigger? Or what does it do if you reverse bias? Does that depletion region get bigger or smaller? Things get bigger. It does. It gets bigger. So it gets bigger. So let's say it goes from here to here. Here's my depletion region. What happens to the amount of current you can have flowing through that N-type material? You limit it, right? It goes down. So if you make the depletion region bigger, you limit the current that you can go down. So you limit the current. So what this does is you can control this. We usually make this a variable battery, or variable power supplies. You can adjust the voltage, adjustable voltage. So you can easily control how much current is flowing. And you can adjust this voltage even by, say, a microphone that puts out a voltage. And as you talk, you're moving the voltage, changing that voltage from the microphone, and it's changing that voltage. You're controlling the current. You're changing that current too, as you talk, for example. So you don't have to have a battery with a knob here. You can have this fluctuating voltage any way you want, and you're going to control the current from a lot of current to a little current. You can actually even stop the current. Put enough reverse bias on there, you'll completely cut off. You have that depletion region where it just completely cuts off the current from being able to flow. Okay? So that's a very useful device to be able to rapidly change how much current you have flowing through something and control it electronically, and that's the transistor. Okay. So we'll talk more about it next time. By the way, Bardeen, when they all won a Nobel Prize for this, Bardeen won another one for what we're going to talk about next time, superconductivity. So he won 2 Nobel Prizes in physics. When I went to I was going to go to the University of Illinois. I went to the University of Missouri, but when I went to register at the University of Illinois, and that was the first day I'd been there, they took me on a tour, and Bardeen was in his office. He was still alive and working in his office, talking to somebody. It was a pretty small office. I was surprised. It was really packed with stuff all in there, so it was kind of neat. It was one of his graduate students that was showing me around. All right.